Okay, so we talked about network solids last week sometime. I'm pretty sure. And we're going to talk about molecular solids today. Molecular solids have a molecule at each lattice point, and they're held together by intermolecular forces. And remember, we've been spending most of this unit thus far talking about intermolecular forces, so make sure you know the different ones. What are some examples of molecular solids?
Well,
Dry ice.
Dry ice, that's a good one.
Whoa.
I'm going to put CO2 in parentheses so we remember what that is.
Sulfur dioxide.
Oh no.
No.
You need to calm down.
No, because remember that that's a network solid. So instead of having a sulfur dioxide, we all heard silicon, didn't we?
No.
We all said no? No.
What?
I heard sulfur though.
That would probably be a molecular solid.
Well, I heard silicon.
I heard silicon.
I heard silicon as well, and so I was like,
I said
no.
Did
I know.
Did I say sulfur?
I know you did.
I said sulfur.
I agree that you said sulfur.
Yeah,
My brain,
my
when the C over here went no, I was like, oh.
Yeah,
silicon.
what's up?
Yeah. Hey, you want beef?
Yeah, I want
I'm not
beef.
sure how easy that is to solidify, but we'll go with it. What's another one that you have seen? Sugar. Thank you.
Wow.
6-1.
C6H12O6. What about wet ice? You know, ice.
Is
Oh, wait.
water wet?
Yeah, let's say dry ice. Like, I feel like we should say the other kind of ice too.
Wet ice. It's wet for 3.
The watery ice.
What does the blue stuff say?
Yeah.
So these have intramolecular forces within each molecule and intermolecular forces keeping the molecules together. It is really easy to mess up on your language with these questions. So the intramolecular force is the bond holding the molecule together. It is a covalent bond. And since tomorrow we're talking about phase changes, let's say they do not break during phase changes. Okay, that just got worse. And intermolecular forces, which attract the molecules to each other. And what are the 3 types of intermolecular forces?
Dipole, dipole, high pH, bonding, and undispersion force.
I heard it all. And these do break, and we'll say break because it's not actually a bond. It's like I didn't learn the last time. How can you identify molecular solids?
By the melting point.
Okay, what is the melting point?
Low.
Pretty low.
Generally low. That doesn't even sort of look like it says generally. slightly better.
There are two L's.
G.
Wow.
G. Nearly.
Love.
You people. Fine. If you want me to actually spell it correctly. What else? This should really say properties, but not melting point. What are other properties you can use to identify them?
Dissolve.
They may or may not, depending on what the solvent is, but they don't conduct electricity.
Could you say that they're crystalline? Does that matter?
Well, they're all crystalline solids, right?
Dude, amorphous versus crystal. Remember the flow chart? Come on.
Yeah, might as well just say they're molecular solids then.
Well, I know. They're actually not, because their melting points are generally low, they're very rarely solid at room temperature. Of our list, the only one that's actually a solid at room temperature is sugar. I actually wasn't pausing for you guys to answer it, I just couldn't remember. It's good when you start a sentence and can't finish it.
You're actually
So-
just saying it so you won't be embarrassed.
Thanks, I appreciate you. So let's talk about ionic solids. It's still
I'm pretty
recording.
naked right now.
Oh, thanks, Sebastian.
Sorry, I had to do that.
I knew somebody was going to have to do it. I kind of thought it would be Parker.
I'm a tame young man.
Yeah. Okay. So ionic solids. You notice molecular solids were pretty straightforward. They're stuff you've kind of been talking about your whole life.
Sorry. Everyone watching the video is just gonna be like, no.
What's wrong with this? This video may need to be slightly edited.
No.
Just keep repeating it then.
I can see the green light.
Okay, I just want to make sure it's not because it does that weird thing where it freezes.
Yeah, hopefully it's not freezing. We'll see.
I have to watch this anyway, so.
Ionic solids have an ion at each lattice point. What are they held together by? Ionic bonds.
Word.
You can't say it like that. You can't say it like this.
It's a day where y'all harmonized with the word.
I know, I wish we'd had that one recorded. We're not gonna try it again though right now. What are some examples of ionic solids?
Table salt.
Thank you. We could name any ionic compound, couldn't we? Like-
Yes.
Chloride.
MgCl2.
Nice.
Oh.
One more.
KCO.
Y'all are boring, not with CLs. How about,
Cesium bromide.
LIVR.
I'm gonna do one with a polyatomic ion, because I'm
Oh.
special.
Wow.
KNO3.
Cesium bromide.
Yep. And the crystal lattice, that is that positive and negative ions surround each other in a repeating pattern. Let's make that a dot, because otherwise it blends into my plus sign. And there are no intermolecular forces. Please do not try to tell me that.
No intermolecular forces?
Because there are no molecules.
Because they're ions. Are we recording?
Yeah.
Now, when you watch the video later, Sebastian, you can count the number of words.
I already started counting and I lost track.
Okay, one more thing to say about this crystal lattice, not about the intermolecular forces, that line looks confusing, is that the crystal lattice is a way for them to maximize the attractive forces between ions and minimize the repulsive. That seems sort of obvious, but I want you to write it down. It's kind of redundant to say forces twice. Sorry. So what do we know about the melting point for ionic compounds?
Way up there.
Very high. Metallic bonds are higher, but very high because the ionic bonds have to actually break. Same thing with the metallic bonds, right? It's very high because the metallic bonds have to break.
How many people in the other class are gone? Are there any gone the other chem class for scholar pool?
No.
Just us.
So hopefully it's only your class watching this video anyway.
I hope
I know
Ryan's
you
is
guys.
it.
I'll make sure.
Speaking of, have we gotten any word about this? Sorry, that's fine. About this volleyball team?
Oh, I do love you. Has anybody heard?
No, I bet you they're losing.
Well, I'm pretty sure one of the web teams is losing right now.
Yeah, at
That's
least
true,
one.
that's true.
There you go.
Can we get a quick shout out to the Bulldog?
yeah, Bulldog.
That's all. That's all. Bulldog.
Okay,
Okay, edit that out.
let's get back to our
Don't.
to chemistry. This is a nice little summary. Honestly, I just put this here for you to review. Review me. And it's got your three, I mean, it's all solids, all crystalline solids, right? Got molecular and ionic off to the right, and then the three types of atomic. It tells you the type of bonding. It says network is directional covalent bonds. That means they go in all directions. Non-directional covalent bonds involving electrons that are delocalized, and London dispersion forces. Their typical properties. These properties are super useful. If you're still struggling with any part of your lab write-up, this may be helpful. Just as an FYI. Also,
I'm sorry, is group 8A just noble gases?
yeah, that is noble gases. If your lab group sat at that back right-hand corner, someone in your lab group is missing their data table. See? You might want to come see if it's yours. Otherwise, you'll be really sad when you try to finish your lab.
The handwriting terrible.
It's mediocre.
Handbook says it's mine. Handbook says I'm right.
Okay.
That's
Oh
right.
my
So-
Oh my
goodness.
god, I'm sorry. Look at me go.
That's amazing.
Here, mark that out and say 18 because we don't use the A and B. Fun. But this is a nice little table that summarizes the information for you. And it's a good table to review before your test. I'm not going to sit here and read it to you because it's a review of everything we've been saying for like the last, several class days. But I wanted you to have it easy to review. So let's talk. In order to determine the kinds of intermolecular forces they have, you need to know if they're polar. And as you learned in the last unit, most of the time, in order to determine if it's polar, you need to draw it, or at least know its shape. So let's do this first one. I bet you know how to draw CO2.
I hope so.
I hope so too. Automatic fail still.
Oh, I see.
Okay.
So we got he's non-polar.
This is non-polar.
That ain't polar.
It's really just textbook non-polar. I mean, just look at symmetry.
Nice use of the word symmetry.
Symmetry.
So what kind of intermolecular forces does CO2 have?
Dipole.
Oh,
Oh, wait.
Only LDF.
Yes.
Now, before you guys are already counting for OCS, aren't you?
Yeah.
Are O and S in the same group? It's gonna look just like CO2, but with one of the O's and S, right? Like that's a fairly logical assumption. It's gonna have the same number of valence electrons. Is it gonna be polar or non-polar?
Polar. No, because of the electronegativity.
Because it's not exactly symmetrical, there will be it'll be a very weak polar, but it will be barely polar.
So it would have a dipole.
So it would have dipole.
LDF.
It's got a little bit of isoelectronegativity.
So, which one has more intermolecular forces?
Definitely the second one.
Okay, can you do that for the next one for me?
Sure.
Absolutely.
I love your positivity.
Where's SE?
And you can see Se and sulfur are in the same group as well, so you can definitely draw one and then like, oh, the other one's gonna look real similar. Oh, I typoed here. I was wondering what the crap that one was. I was like, I don't know what H2CP is, but that's a weird compound. It's a typo. If you get to the third one, it should be H2CO. Sorry.
I keep thinking this is the last class, but it's not.
It is very sad.
You're right.
How do you draw that?
Never mind.
Well, I counted electrons. Selenium has 6.
20.
Yeah,
Yeah.
that's 20.
It should be 20.
So shouldn't it be a double bond? On one
There
side?
should be one double bond, right?
Yeah, it's a resonance structure.
Oh,
Michael,
well, yes. Thanks for, see, I was just seeing who's paying attention.
It's resonance, right?
It's a resonance.
Yeah, it's a
There is a
resonance.
resonance.
Yeah, it's a
Do we have to draw both?
Did I draw both?
Michael was
Um,
right here. It doesn't look like it. Yeah, it does. Look, that's resonance right there.
I mean, now there's a double bond.
Yeah, it was double bond.
How about we do this? Is it gonna freak you out if I swap the thing?
Yeah.
Okay, then don't write it that way on your paper. It's probably gonna freak out the people who aren't here too.
That's gonna,
Just write down resonance.
it's a resonant of itself.
It's kind of freaky. I think they got it.
Okay. What kind of forces do these both have?
LDF.
LDF and?
Dipole.
How do you know which one has more?
Electronegativity.
Which one has the bigger electronegativity difference?
As you know.
So it's gonna be more polar, isn't it?
Yeah.
Good. Oops. Try the next one. It's okay. Have fun watching the video later tonight, Sebastian.
Were you ditching class?
Yeah, amateur ruins.
And he announces it publicly to the class too before he does.
Wow.
No.
Okay, hey, did you draw these?
No.
Why not?
Just because I didn't get to it.
Okay, we'll draw them real quick if you feel like you need to.
Probably don't.
Wait, so we said which one was greater on the top one?
SeO2.
That's because dipole gets more polar.
Mhm.
That's because polar has like.
Because it's further apart on the periodic table.
So.
Cut this out, it's sassy. Oh, I mean, you really tested it.
Okay.
Oh, because there's 14, so two.
Oh, okay, I was about to say, it's because phosphorus has 5 and there's.
Well, remember I told you to fix it because it was a typo.
Yeah, I'm just.
Sorry. Okay, did you actually have to draw these?
Probably not.
No.
Why not, Maggie?
The hydrogen bonds.
Because you know that one of them has hydrogen bonds and the other one does not.
Right.
You know that those H's are on the C because of the way the formula is written. And because you can pretty much guarantee that the C is in the middle. So this one wins because of H bonding, but it's good practicing. So now we've talked about which one has the most intermolecular forces, but I've also already straight up told you that the AP test is not going to ask you which one has the most intermolecular forces. It's going to ask you about something else. So here's another summary. When the intermolecular forces increase, does boiling point and melting point go up or down?
Up.
I'll write the word.
I drew an arrow too.
Yeah,
I
but-
should write it too.
What about viscosity? Does it increase or decrease?
Increase.
What's vapor pressure? Did we talk about that yet? I feel like we did. Are you sure?
I don't think we did.
What do you think it is?
The pressure when you turn it into when you vaporize it.
It's actually the pressure in a closed container of the vapor above it. So if like you put the lid on my container, there is some water vapor in the air up here, right? So the pressure of that pushing down on the water is the vapor pressure.
100% decreases.
I agree, it's gonna decrease. Because if the intermolecular forces are stronger, then it's harder for it to vaporize. So there will be less vapor pressure. It's the only one that decreases. We're gonna talk about vapor pressure a lot before the end of this chapter. I just couldn't remember where we did it. So this is a good summary of how we're using all this information.
Next.
We're gonna start talking about phase changes really quickly because it's a really, really long bit of stuff. And we're getting to do some math.
It's like the MCAT, the Q.
We get to do MCAT soon.
What is the
Tomorrow.
No.
Remember that curve where you had to do like
Yeah,
Yeah.
boom kind of thing?
That's
Yeah.
cool. Yeah.
That's what we're doing.
it is.
Oh,
Okay, vaporization. What does vaporization mean?
Vaporize.
How much energy is needed to turn it from liquid to gas?
That is the enthalpy of, or heat of vaporization. I agree.
Oh.
What does it just mean to vaporize something?
Turn it
into
into
gas
liquid
from a
gas.
liquid.
Liquid to gas. I mean, I was like, you're saying good stuff. It just wasn't quite what I was.
I was just ahead of the game.
I just gotta, like, get my handwriting better.
That's right.
Typically, they'd rather be just ahead of the
Yeah.
game.
First time.
I'm not laughing at you, I'm laughing at you.
Yeah.
Okay, and there are several different terms. There's boiling and vaporization and evaporation. Everything is vaporization. Boiling is a type of vaporization. Evaporation is a type of vaporization. The difference is evaporation happens at the surface. Boiling happens throughout all of it. So boiling, the gas molecules can be anywhere within the liquid. Evaporation only happens at the surface. So make sure you use those words correctly. And any liquid will have some vaporization happening. Oh, that's what I'm saying. That's all liquids evaporate at all temps at least a little bit. Bless you. All temps where they can exist as liquids, right?
It's just how much they evaporate.
Mm-hmm. And hopefully you can already predict that things that evaporate a lot are things that have less intermolecular forces, which is why they have greater vapor pressure. And we're going to talk about this term, delta H of vaporization. I feel like we have talked about it a little bit. But it is the energy change associated with vaporizing 1 mole of a liquid. We generally do it in kilojoules per mole. I have to zoom in a little bit. It is endothermic. Why is it endothermic? takes energy to change the molecules, which means that these values are always positive. And usually the units are kilojoules per mole. It can be given in joules per mole, but it'd be kind of jerky. Can you get out your calculators? Let's do a practice problem. I know we haven't had math in a while, have we?
Fun game called Fun.
If you don't have a calculator, I have some. I was gonna say several, but then I felt like that was an overestimate. I've got one here and one there if you need them. Did you not just come from a math? Never mind. You're not allowed to use calculators, are you?
We did today, but.
Okay. You're just lazy then.
It's rare.
No, I went to home. Or somewhere. I think it's
And
broken.
you people had to work with him? Sorry.
I'm sorry, but I like answered like most of that.
Did you?
No, of course not. Read it.
Do you know how to answer this?
Oh, yeah.
Okay.
CMAT.
It's like me monthly.
No.
No, it's
No,
definitely just a
what?
stoichiometry.
It is just
Yeah.
stoichiometry, isn't it?
Logic.
What idiot would say CMAT?
You did.
Well, you just wanted to make sure no one else was thinking that.
Exactly.
So this is just a conversion factor. That many kilojoules per 1 mole, you can just put that right into your stoichiometry, honestly.
That's what we're doing.
5.28.
You're terrible. There, I heard the right sig figs. Thank you, Lucas.
Ooh.
I don't even try to do sig figs at this point.
I think you might have had your molar mass of water wrong.
Did I?
No, not you, Maggie.
I think that's
Yeah.
the first time I've ever gotten sig feedback. Yeah.
Nice.
Okay.
It only took you like 3 years.
What?
Really?
Just giving us some of your mixtape. Is this sneak peek?
Okay, so that gets you grams of water. And I want mole on the bottom. So 40.66 kilojoules. And I end up with 11.3 kilojoules of energy. Does that make sense?
Yeah.
You have a few of these calculations on your Quest, the new Quest that opened up today, by the way. Be careful with that. Just because there's 2 open, for you. The one that opened up today is due like the 5th, which is Thursday night afterwards. I do not intend for you to have to do any work on it over Thanksgiving. You may want to do like 10, 15 minutes tonight so that you're not slammed that week after Thanksgiving, because you know that every class is going to have tests coming up, right? So you may want to do a little bit ahead. I don't care. But I'm trying to plan so that you don't have to work over Thanksgiving unless you just really feel the need. I want to do one more slide, because this goes with vaporization. So when you have liquids in a closed container, when you first put the lid on, there's some initial vaporization. I mean, there's always vaporization. But when you're like talking about vapor pressure, so there's some initial vaporization. Feels like too many I's in that word, but. And you have seen this before. If you've got a closed container, if I left it in my hot car, when I came back, there would be condensation all over the inside, right?
Mm-hmm.
Because some of that would recondense. Oh, that's backward, isn't it? Yeah. If I left it in the cold car, that would be better. Cold car. Because it just recently happened. Okay. If I left it in the garage overnight and I got into my car and it was all cold, there would be a bunch of condensation. So as there's vaporization, there is stuff being recondensed, but it waits until like it reaches the right pressure. And so it becomes a dynamic equilibrium where some is being evaporated, but then some is also being recondensed. So it's kind of always happening. The reason why if you leave a beaker out on the counter, it'll get lower and lower and lower is because that vapor can't be trapped to recondense back in the same container. It may be recondensing somewhere, but not necessarily in that beaker. So eventually, evaporization and condensation occur at the same rate. Which we would call an equilibrium.
Doesn't that depend on temp though?
It does depend on the temperature. I agree.
Does hexane have really low intermolecular forces?
Ridiculously low intermolecular forces. It is small and nonpolar. So it doesn't have anything but London dispersion forces and not very strong London dispersion forces, which is why I just let the beaker evaporate back there. We will talk more about this tomorrow, about this equilibrium and vapor pressure in general, and a little bit more about changes of state. We'll see how far we can get with that. Like I said, you may want to work on your quest a little bit. You probably want to work on your lab notebook a little bit. It's due the Thursday after we get back. Again, I just don't want you being crazy. And you have a bunch of, or you have that essay due, right? Please don't forget the essay.
When is the essay due?
The Wednesday after Thanksgiving.
Wednesday, Thursday is rough.